Hi, everyone. Thanks for joining the Streaming Improvements for Dense World presentation. I'm Richard Malo, Principal Engine Programmer at Epic Games.
And I'm Jarosław Rudzki. I am Core-Tech Engineer at CD Projekt Red. Before we will continue, I would like to give a special thanks to Sebastian Lucier and Ben Ziegler from Epic Games, who also contributed to this initiative. We have quite a big agenda today. We have quite a lot to go through. We'll start with short streaming overview, and then we will go through all the changes, starting with mutators, cell transformers, new hash sets, and new features that allowed us to get much better results, like async physics state creation, the unified streaming budget, to finish the whole presentation with Fast Geo and simplified mesh and texture streaming that are new development and experimental. But to start with explanation that we work together because there is no better way to build new things and push boundaries than working on something that tries to do things that we weren't being able to achieve before. At CDPR, we partner up with our friends at Epic with ambitious goal of building the tech demo that will showcase the Unreal Engine running open world experiences at 60 FPS on current gen consoles. And today with Richard, I will be very happy to present all the streaming improvements that allowed us to make that happen.
Okay, so before diving into the streaming improvements, let's begin with a quick overview of how the world partition streaming generation process works. So the process is designed to break down large worlds containing vast numbers of actors and sublevels into efficiently streamable cells. The process runs both during map cooking and whenever Pi is launched, so it must be efficient. And since world partition uses levels as containers for actors and relies on level streaming to load and unload them, the process needs to generate levels. So it takes as input, of course, the world partition setup, including the grid setup, and a subset of the actor's information, such as the actor's streaming bounds, runtime grid, specially loaded flag, and runtime data layers. This information is accessible through the asset registry and is updated each time an actor is saved. So we call this information the world partition actor descriptor. So when launching Pi or cooking a partition map, the streaming generation process starts by building a list of all the world partition actor descriptors of the world. It then performs a validation pass to detect, report, and correct all the errors and ensuring the content is valid for the partitioning phase. And then the runtime hash handles partitioning using the world partition setup and the provided actor descriptors. It will then create the necessary world partition cells and distribute the actor descriptors in the generated cells. And then a level will be created for each cell. Actors will be loaded and moved into the level. And when cooking, the level package will be saved, and in Pi, the level will be transient and only be created when its cell needs to be loaded.
So with that introduction, we need to first discuss what we want from the streaming as a developers in the first place. The streaming has to be flexible because we all have different use cases. But in all, we strive for memory optimization, and it has to be performant, so we can ensure that the players can move around freely without any distractions as much as possible. The execution has to run within the budget. And the budget we assign for the streaming, it has to be respected in all cases. If not, player will encounter traversal stutter or we have to plan for loading screens. But to achieve it, we have to ensure that we have tools to build with higher granularity and allow iterating on it without breaking what we built before. Worlds that we build are not uniform. They vary in density and vision range. So the streaming has to allow us to maximize the effectiveness of engine in different scenarios. We would like to remove as much of the things we have from critical path, so things like streaming especially don't contribute to that final frame image. And we hope for a renewed look at simple primitives, so we can have spawning and adding objects to the scene cheap again. But all the things we build, since we all have different use cases, they has to be optional. But also, it is good when they are open, because they will allow us to experiment with novel approaches to the problems we have. For the last year, I had the pleasure to work with Richard and Epic World Building team to address some of those issues. And I'm thrilled today to put the lights on the improvements we did together.
So starting with the 5.4 releases, we started introducing new features aiming to provide users with greater control over the streaming generation process. We added actor descriptor mutators, a new runtime hash set, and runtime cell transformers. So in the pre-partitioning phase of the process, actor descriptor mutators were introduced to enable modification of actor descriptors of the world. They allow to automate tasks that previously would have required a builder, but without having to check out, modify, or submit content. This process is non-destructive and it's code-driven, which makes it much more reliable and robust than manual editing. The mutable properties are the specially loaded flag and the runtime grid, and we plan on supporting other properties to be mutable in future releases. And after the mutation of the actor descriptors, the streaming generation process does a second validation pass, which will again detect, report, and correct any errors that could have been introduced by the mutators. A common use case for actor descriptor mutators is automatically assigning actors to a runtime grid based on criteria such as the actor location, bound, name, actor tags. In fact, any combination of actor descriptor properties can be used here.
So for us as game developers, the mutators allow to answer the question of the word composition. At CD Projekt Red, we heavily utilize the folder structure to separate architecture from decoration, vegetation, and so on. With vanilla approach, we would have to do a manual pass to assign proper grids for specific assets. With mutators, we can automate this process. This means we can iterate. We can very easily split existing structure and separate decoration into even more detailed grids, like depending on the size or the draw distance, or whatever comes to mind, and compare the results. So let's see it in action in our well-dressed market. Here we are seeing the full scene with all the details you expect to have when you walk through the street. Right now, we remove decoration layer, and now architecture. The only things that you see are the NPCs and the gameplay elements, like the ladder used by one of the NPCs or the market stand. For all those improvements we are going to discuss today, I will try to get back to this scene where we spawn all our NPCs and we walk through the market. Thanks to mutators, we easily split our world into very detailed grid setup. And thanks to that, we can load fewer primitives at one time. It significantly impacts the memory consumption, but also the performance. When it comes to performance, I will try to showcase it, as mentioned, on our market bit. And here you see the critical path, the update level streaming, and how much time it takes on a CPU to add 2 bits of the level to the scene. With mutators, we increased streaming granularity. This means we split the big chunk we had in the middle of the graph into smaller sections that we stream in different frames. But we split them not only into smaller chunks, but we also stream in different physical spaces. So they are split in frames and by physical distance.
So if we go back to the streaming generation, in the partitioning phase, starting with the 5.4 release, we introduced a new runtime hash set to replace the original runtime spatial hash shipped with Unreal 5.0. This new hash supports 2D and full 3D streaming and contains a list of partition objects. Actors are mapped to their corresponding partition object based on their runtime grid property, and the partition object can parse that runtime grid property to implement specific sublogic. We provide two partition objects, the loose hierarchical grid, which is the default partition used when creating a new map now, and the level streaming partition, which can be used to mimic standard level streaming or even world composition setup quite easily, with automatic support for distance-based streaming, HLOD, and runtime data layer supports. This new hash effectively decouples the partitioning from the common logic, like handling runtime data layers, and makes it easy to write new custom partition object.
In case of our demo, you can see it in action in our distance shot. When the camera rises above the landscape, we can stream out all the environment bits that are below us.
And then again, in the streaming generation process, in the post-partitioning phase, starting with 5.5 release, the runtime streaming cell transformers were added to allow transforming the generated world partition cells. Again, this is a non-destructive process, and it's data-driven. It can be configured in the world partition setup using a runtime cell transformer stack. So a world partition cell is transformed by each runtime cell transformer as it progresses through the stack. And the runtime cell transformers have limitations. You can modify the world partition cell level's content, like adding, removing, modifying any actor or component part of that cell, or you can even create embedded asset inside that level. But what you can't do is modify the persistent level content or generate new world partition cell, as this is a post-partitioning process. You also cannot create public assets. And with the runtime cell transformer framework, we provide the ISM runtime cell transformer, which automatically transforms static mesh actors into instant static mesh components. And it's also possible to visualize the transformed result using the provided actor coloration mode. And in the transformer settings, you can specify a minimum number of mesh instances required to allow the transformation and define a list of allowed and disallowed actor classes. And this transformer has some limitation. It doesn't support replicated actors. The root component mobility needs to be static, and child actors component are not supported. So we encourage you to experiment with and implement your own runtime cell transformer based on your project-specific needs. But be careful. This is a powerful tool, but it comes with some risks. And no validation is performed by the world partition streaming generation process at this stage. That means it's possible to introduce issues. However, it's important to note that this only affects runtime behavior. So editor content remains unaffected, your source asset and level data are safe. We also recommend adding debugging tools like logging, debug display, anything that will help you understand how the content was affected by the transformer. And to implement your transformer, you simply need to derive from the world partition runtime cell transformer class, override the transform methods, and insert your transformer in the stack. Some ideas of transformer: you could have a transformer that generates optimized collision for your cell, or generate instance actors, or generate an actor using a custom component that already supports instancing.
And we are going back to our market scene. We see the results of transformer that converts the static meshes into ISMs. Once again, we see fewer primitives as we merge components together, and we see reduction in memory. While previously we just split the big level into chunks, these times we get real performance savings. Due to fewer components, we have fewer loads, post-loads, spawns, and destroys. And with increased streaming granularity, we just optimize the content we have. So now it's the right time to look into what is so expensive in the process of streaming. With component reduction, due to conversion to ISMs, we minimize the cost of registering those components. What we find instead is that the majority of the cost comes from streaming and creating physical state of the assets.
So this is why, starting with the 5.6 release, we implemented asynchronous creation and destruction of the physics state. In addition to the changes made in Chaos to support this, the level streaming, more specifically add to world and remove from world, was also updated to support asynchronous task management. We added incremental pre-register and pre-unregister component phases to handle the asynchronous creation and destruction of the physics state. And the supported components for now are the static mesh component, the ISM component, and the landscape height field collision component. Well, remember, this feature is considered experimental in 5.6, but to enable it, you simply need to turn on these three console variables. And after enabling this feature, we see that the creation of the physics state now runs in a background task. So adding support for asynchronous tasks in the level streaming introduces some latency in add to world and remove from world. While the level streaming is waiting for the asynchronous task to complete, it will not try to process other levels. This means that we're potentially not using the entire game time budget. So we have two options. Either we don't use the whole time budget, which is fine, and wait until the async task completes, or we try to maximize the time budget and start processing other pending levels to be added or removed. So to make the second option possible, we added support for adding and removing multiple levels concurrently. And these are the two console variables to set up. Here we can see that multiple add to world and remove from world calls were initiated within the same game thread time budget, and however, none of them actually completed during that frame. Instead, they each kicked off asynchronous tasks, and most of them will likely finish on the next frame.
And we're going back to performance of our market bit. We have made performance optimization on adding and removing bodies from the physical scene, but the main gain comes from moving heavy physical creation and destruction from critical path to the worker thread. This means that as long as you have spare cycles on your worker thread, you're gonna see significant improvement in streaming. Here, a bit different scenario where we load multiple levels in sequence. Without async physical state creation and destructions, those levels are piling up as the streaming is trying to catch up with our movement. With asynchronous physical state creation, the system has a better chance to catch up with movement of our character. So with heavy physics removed from the critical path, we had to look at the streaming process as a whole again. Going back to our mission statement, we wanted to build a demo that runs at 60 FPS. And to implement something like that, the most important concept is budgeting. In open world experiences, we need to ensure in every single frame that we keep a budget for streaming, a buffer. Because if there is no buffer, when you need to stream something in, you will encounter the traversal stutter. We do not stream in every single frame, so making this budget big will waste cycles in all those frames where we just idle. But if the buffer is too small, if we will try to make a buffer small to spread it over more frames, we may stream too slow, and due to streaming granularity, the budget might not be respected when we initialize very heavy objects. With base implementation, we need to worry about 3 of such budgets: There is one for add to word, there is another for remove from word, and finally, process async loading, as they all might execute, as showcased, in exactly the same single frame. In case of our demo, we initially had to reserve 2.5 milliseconds for all those budgets. This represents 15% of every single frame. This is quite a lot. We had to step back and look at the streaming process from the distance, from perspective not of one frame, but multiple frames, and retrace how the engine behaves while we play the game. And instead of looking on one timer, let's see what is happening in multiple. So we will try to look what is happening when we load this small bit of the level. Everything starts quite early with very cheap request to async loading to load all required assets, serialized actor component information. For that specific portion of the level, it just takes 5 frames to load needed data from drive. But even as those assets are being loaded, we need to run post-loads that are executed on the game thread. Depending on the asset types, those assets might need to execute post-load functionality or initialize rendering resources. Since we run with very tight budget of just 0.5 milliseconds, it takes 29 frames or around 500 milliseconds to process all that data. And after we'll finish with processing, we start adding loaded actors and components to the word. And once again, with quite tight budget, 1 millisecond, it takes 24 frames, 400 milliseconds to add those elements to the scene. Since there is a small overlap in the middle between those two processes, there is 51 frames of delay between our request and the final update for the scene. The worst part is that in most frames, when we process async loading, we waste all the budget for add to word. And when we are adding to the word, we're wasting all the budget for processing. And for the whole duration of this example, we wasted the whole budget for removal, but we still had to guarantee all 3 of them. We are utilizing just the fraction for the budgets that we had to assign. For that reason, with Ben Ziegler, we have implemented an optional unified streaming budget. We calculate streaming budget as a sum of existing budgets, but we still execute process async loading with guaranteed process async loading budget. Then, we've unified budget left that will measure how much time has passed since we entered this functionality, including process async loading. We will start update level streaming that will now execute add and remove under single time budget. The update level streaming will be longer if we had fewer process async loading than the time allowed, or it will be shorter if async loading went over the budget. And at the end, we check again if the update used all the budget that we assigned to it. And if not, we will try to run process async loading again to prepare next batch of assets to be ready for the next frame. The whole functionality is extremely simple, but with that change, we could actually reduce the budget assigned to the frame from 2.5 to 1.5 milliseconds. And still, we got 40% reduction in streaming response delay. In all the frames, when we don't add or remove from the word, process async loading gets huge boosts because it can use the full budget just for processing. This will be beneficial not just for streaming, but for every functionality that requires loading assets on demand. Add and removing gets boosted when we finish with process async loading. And the cool thing is that any hitch in process async loading will be amortized in that specific frame by reduction in time in update.
So again, taking a step back and let's look at the performance again, we see that streaming static geometry, such as HLOD actors or even the transform ISM actors, go through the same registration process as more complex game actors like gameplay actors. However, static geometry is much simpler, so it really doesn't need that kind of overhead. So what we should aim for is to remove the static geometry from the regular actor component registration process and stream it outside of the critical path. This should have no impact on the editor workflow and should also preserve full world partition functionality. This fast path should be easy to test in-game and support quick iteration with minimal setup. This is what led to the development of the new experimental Fast Geo Streaming Plugin. The plugin consists of two key components, the content generation and the runtime streaming of that content. And to generate the Fast Geo content, this process should first extract the static geometry and convert it into a lightweight non-new object data structure. That content should be stored in the same level as the non-transformed content, as we need both of them to stream at the same time. And the process should be non-destructive and shouldn't require an offline process like a builder to generate the content. This is a perfect use case for runtime cell transformers. This is why Fast Geo comes with its own runtime cell transformer. It's configurable through the transformer settings or via code if you want to override the default implementation. Actors can be partially or fully transformed, and the fully transformed actors are simply removed from the level. Note that this transformer doesn't automatically convert static mesh actors into ISM components, but to do so, simply add the provided ISM cell transformer before the Fast Geo transformer in the transformer stack, like we see here on the right. As for the runtime streaming of the Fast Geo content, the level streaming was modified to allow custom streaming when levels are added or removed. And Fast Geo streaming relies on the new asynchronous physics state creation instruction, so this chaos CVAR needs to be enabled. Several systems were adapted to support decoupling from actors and components, more specifically the rendering, the physics, the world partition HLOD subsystem, and the render asset streaming manager. On the rendering side, we built on the work previously started with render proxy decoupling. On the physics side, we decoupled the async physics state creation and destruction from actor components, and we also provided a physics body instance owner interface on the hit result and the overlap result. We also decoupled the HLOD subsystem from HLOD actors. And finally, the render asset streaming manager was also modified to work without primitive components, but this topic will be covered later in the presentation. Here's an overview of how Fast Geo runtime streaming works with the level streaming. So when adding a level to the world, Fast Geo streaming is notified, finds its Fast Geo content inside the level, and starts asynchronous tasks to create the physics and the render state. While these tasks are running, the non-transformed actors and components are registered using the regular registration process. A new delegate was added to allow external systems like Fast Geo Streaming to monitor their internal tasks and report whether they have completed. And then add_world will combine that result with its own internal state to determine when it has completed. And note that remove from world uses the same pattern. Fast Geo currently has some limitations. You can see a full list here, though I won't cover all of them now. However, a few worth mentioning are replicated actors are not supported, as Fast Geo doesn't handle replication right now. Blueprint actors with logic are excluded from transformation to avoid potential gameplay issues. Actors referenced by non-transformed or partially transformed actors are also excluded from transformation, as this would break actor references. And actor components mobility needs to be static. And to aid in understanding what was transformed, what wasn't, and the reason why, Fast Geo comes with debugging tools. We added a Fast Geo actor coloration mode, which will show in red the non-transformed primitives in the scene. A console command was added, fastgeo.show, which allows to hide or show the Fast Geo content. It's an easy way to isolate the non-transformed content in the game. And we also added debug modes to report in the output log all the details of the transformation and the reason why some actors or components were not transformed. There are 3 debug modes. The first one is based on the selection, which is what we see here on the right. It will simulate the transformation and log the result based on the selected actors, which is pretty helpful in the editor. Another debug mode will log the transformation details of a world partition cell every time Pi loads and transforms that cell. And lastly, a console variable was added to allow logging of the transformation details per cell during cooking. Here are all Fast Geo console variables. Those listed in the performance settings sections allow better control of the budget and the speed at which things are being added to the scene.
Okay, so we're going back to our demo, and here are a few examples how the Fast Geo impacted our project. So first, the forest area. Almost everything gets converted to Fast Geo representation. In the market, very similar situation. The things that we see, the things that were not converted are the things that are not supported, like skeletal meshes, gameplay elements, and the things that do not have static mobility. We've been able to convert 91% of all components we had in our demo. 86% of actors were fully transformed, and 1% was transformed partially. When it comes to the performance, we see yet another reduction in memory. This is due to conversion components and actor to very simple primitives. On performance side, we have the graph with all the transformation we did so far, but let's focus on those 3. Fast Geo greatly impacts performance because we don't have to load and post-load and create all the components, run all the registration for the environment that doesn't have to have it. Here we showcase the data with our base setup, but in final demo, the whole budget for the streaming was just 0.8 milliseconds.
So we also enabled Fast Geo in CT sample. Naturally, this project is an ideal candidate as most of the content was already compatible with Fast Geo and didn't require any modification. So some interesting numbers here, and we didn't modify the content here. 92% of the components were transformed, 94% of the actors were fully transformed, and 3% were partially transformed. While we don't necessarily expect projects to reach that level of coverage, it still serves as a useful reference for what to expect when enabling this feature in your own project. And then we ran an automated test on PlayStation 5 with the drone flying through the map at its current maximum speed, which is around 215 kilometers per hour. Sorry. And the streaming settings were tuned to minimum values to prevent hitches caused by slow streaming. And these metrics highlight the impact of enabling Fast Geo. As expected, we see that add to world and remove from world now take a very small amount of time on the game thread. And since a big part of the map was transformed into Fast Geo content, we end up with a lot less U objects, which translate to less objects being processed by both the garbage collection and the process async loading. And here's another view that shows how little time we now spend in add to world with Fast Geo. We see similar result with remove from world and for process async loading. And here we see that both the peaks and the duration of the garbage collection were significantly reduced. We then extended the test further by increasing the drone speed to 540 kilometers per hour while maintaining a very tight budget of just 0.2 milliseconds for add to world and remove from world. In this test, the drone acts as a spherical streaming source and blocks on slow loading. What you see on the left is the result without Fast Geo. The game can keep up and pauses while streaming catches up. On the right, with Fast Geo enabled, streaming stays ahead of the game, keeping everything smooth and uninterrupted.
So, during my and Richard's work on streaming, budgeting, granularity, we realized that we missed crucial part of the streaming: texture and mesh streaming, or more broadly speaking, streamable render asset streaming. This is legacy system that streams MIP maps and LODs for static and skeletal meshes. Not to be confused with virtual textures and Nanite as virtual geometry system. Texture and mesh streaming relies on scene information. It is very CPU intensive process. Each time we load the level, the system has to extract all the actors from all the levels, and it has to extract all the components from actors and from components, textures from materials. There is quite a lot nested loops. I will not get into a lot of details here, but just so you understand, for each asset, it has to manage and keep track of the bounds of all components that are using that specific asset to estimate screen space projection of that asset so it can load a so-called wanted MIP with respect to the texture pool size. The costly registration to that process is on our critical path on the game thread. In case of our demo, we are using multi-layered materials, and each material can have over 30 reference textures. We have textures that might be referenced by thousands of components in case of foliage, or they might be referenced by just hundreds in case of our environment and architecture kit. And not every use case can be efficiently supported by virtual textures, but I recommend using them whenever possible. We have to stream MIP maps to efficiently use the high-resolution textures in our games in all the places where they might have impact, but we won't be able to keep them all loaded at all times to the memory. We realize that this is yet another budget that we have to ensure on our critical path. We have to guarantee that the frame rate is smooth when we stream the level. But despite of our hard efforts to tweaking it, we've had very hard time to ensure that it runs with reasonably small budget. We implemented texture sampling streaming cache to break one of the most expensive loops, to retrieve the sampling information and the whole list of the textures. With console variable, you can enable it in your project. And we added parallel processing, but not whole algorithm were susceptible to parallel execution. But even with additional CPU power, we had really hard time to reduce those spikes below 1 millisecond. And that budget for 16.6 millisecond frame felt way too big. With all previous efforts, we always tried to first optimize and then remove things from the critical path. And this system felt like a good candidate to rework as well. And with introduction of the Fast Geo, we had to think how we can support objects that are not uPrimitive component based. We decided to implement additional module to render asset streaming manager, so-called simple streamable asset manager. If you use Fast Geo and you need texture and mesh streaming, you will need to enable it via project configuration. It replaces component-based registration process with the process that is relying on a scene proxy. But it can be fed with any arbitrary data that can provide all the necessary information. The cost of registration was removed from critical path. We integrate the new system with the scene proxy because if you want to put something on a screen, you will have one as well. All the processing done with simple streamable asset manager is executed asynchronously in the background. Due to simplified nature, the asset manager has better memory access pattern and can process data a bit more quickly. That significantly reduced our cost of calculating wanted MIPS. I highly recommend to check this module in your project, even if you are not using Fast Geo.
So here are additional streaming-related improvements introduced in the 5.6 release. The world partition update streaming state now supports to run asynchronously. This is the process where world partition decides which shell needs to be loaded, unloaded, activated, deactivated. Similar to begin play, end play can now be done incrementally during remove from world. This allowed to better respect the game thread time budget. We also added the possibility for primitives to be added to the scenes outside of the game thread while registering the component in the game thread. And finally, we added caching of ISM component bounds at cook time, which reduces the component registration time.
We have also some ideas for future research. The Fast Geo remains in active development with ongoing improvement plan, like support for more primitives or support for movable objects. The mutators, they might allow us to mutate more properties, like maybe they could resolve the HLOD assignment process for us as well. And with more advanced transformers, we might be able to separate the collision representation and graphical representation of the level and put them into two separate grids to stream them separately. And despite our improvements, the texture streaming process is still very CPU heavy. The estimation for wanted MIPS are very optimistic, and with sampler feedback, we might get much more detailed information that would allow us to be even more aggressive when it comes to memory pool sizes. When preparing this presentation with Richard, we knew that it's very packed and it has a lot of information that you will have to process. So we prepared this one slide that will try to sum up all those bits with one sentence. We implemented mutators so we can automate word partition, the runtime hash set to stream in 3D and allow us to experiment with new strategies. The transformers will help us optimize content we build, and asynchronous physics state creation moves all the heavy processing to the workers instead of dealing with it on critical path. Unified streaming budget allows us to worry about fewer budgets and it helps us to efficiently use those that we assign. Fast Geo to stream static geometry more efficiently. And finally, simple streamable asset manager to execute in the background so we don't have to worry about it. So thank you all for attending this presentation. A special thanks to my colleague Jaroslav for his valuable contribution. And we invite you all to try out all these optimizations and share your feedback with us. And I want to thank Richard and our friends at Epix for inviting me here today. I feel very honored and I'm very proud with the work we did together. And I must admit, I'm very excited to see what ideas you all gonna have and how you will utilize those tools. And remember to share that knowledge with us as well. Thank you. Before we leave, here's a quick link of the world building guide. You can find all the details on the new features coming up in 5.6. And Jaroslav and I will be on the Dev Hub. If you guys want to ask questions related to this presentation, we'll be available just after this. So, thanks again. Thank you.